Welcome, everyone. This is the Transformative Vertical Flight Working Group 4 Public Service Meeting, number 80. Today is November 16th, 2023. Welcome and thank you for attending. As usual, while we are allowing a little more time for the additional attendee to sign in and log in, let me go through some routine information. One of the things is about some of the coming conferences. Just a reminder, in case some of you are attending. One will be the first international conference on advanced air mobility system in India, which is coming up in December 4th to 6th. So if any of you guys are attending that one, it'll be very interesting to get some feedback on the next meeting. And of course, there's one in the European rotors, one of the large significant event for Rotorcraft related activities and conference taking place end of late this month in Spain, Madrid. And following that, coming in January, there is a significant meeting. It's 2024 AIAA Science and Technology Forum Exhibition, the SciTech Forum, which will take place in January 8th to 12th in the Hyatt Regency in Orlando. I'm planning to attend there. Always a lot of interesting technical discussion and paper and so on. And also quite relevant to our working group, and hopefully, of course, as everybody realized that this meeting are not limited to working group 4 public services. We're working group 1, 2, and 3 are all invited. So good to have you guys. The coming up in February, it's the Transformative Vertical Flight 2024, 11th Annual Electric VTOL Symposium, as well as the 6th Vertical Flight Society Aeromechanics Conference. That will be February 6th to 8th in Santa Clara, California. I hope to see some of you there in person. And also, there is a technical meeting on development, affordability, and qualification of complex systems, organized by Vertical Flight Society. Will take place in February 20th, 21st in Huntsville, Alabama. Close to me, so we'll try to be there. And there's one more Aerotech by SAE in March 12th to 14th, will take place in Charlotte, North Carolina. I have always enjoyed the meeting there. It's a broad-based from highly technical discussion to application and actual applied engineering. So a very good conference. So anybody interested, don't miss that. And with that, I'm going to get back to introduce our today's speaker. Welcome, Rodolphe Boulais. Oh, there you go. Right. All right, thank you.
No worries.
He's technical lead emerging aviation product at Saft USA. I'm aware of Saft in my past work, but glad to see them putting so much effort in this space. He has over 31 years of various positions in the battery industry as a quality engineer, manufacturing supervisor, project engineer, and application engineer. He contributed to various branches of the industry, from technology transfers, process improvement, to battery design for electric vehicles, telecommunication, and aviation market. Today's presentation is packed with a lot of information, a lot of content, and so I want to leave.
You keep it light, yeah.
I want to leave Rodolphe as much time as possible to cover instead of being rushed. So take as much time as you need. Feel free to, and folks, if you have any questions, feel free to bring it up or typing in the chat room. We'll try to cover those topics. Either, well, it's up to you how you want to handle it. It can be in the middle or at the end. Leave a little time for Q&A. So, floor is yours.
Thank you very much for the introduction and the invitation to this group, Johnny. It was my pleasure meeting you in Bremen, in Germany, last September. I'm going to share my screen. That's me. I think you have to. Can you unshare your screen? Now, we'll start with other participants. It still won't let me share for some reason. There you go. Oh, still not. I think so. Yeah, where's the? There you go. So good afternoon and evening for European speakers. So Rodolphe Boulais, I was presenting, and we met with Johnny at the Bremen Electric and Hybrid Conference in Germany last September, and Johnny kindly invited me to represent part of this material. So this Saft is developing technology for the electric aircraft and propulsion. We have extensive presence in the aviation industry for the past 80 years, and continuing to offer over 20 years of experience in lithium-ion technologies in the industry of aviation. So I'll turn off my video to protect some bandwidth, and hopefully the presentation should go smoothly. So we'll review a little bit the prospect of the advanced air mobility, and very briefly the roadmap that drives the opportunity of the advanced air mobility, which is directly in line with your activities. The opportunity and the application landscape of the energy storage systems, and the subsequent lithium-ion technology that are available to the industry and to the application right now. And with so you have all the reference are placed inside the slide, the PDF that you can have, and and this is at the end of the document as well. So really, as we saw during in Bremen, you know, the desire to reduce carbon neutrality is very strong in the aviation industry, and this kind of graphic we're very prominent during the conference on how to obtain carbon neutrality, different path. The electrification of aviation is one of these paths, and one of those paths, and all the work being done today will accelerate this implementation, so that we can not only work on efficiency with the more electric aircraft, but also in and not have to reduce too much to be frugal and by reducing a lot of flight activity, by to continue to enjoy our mobility and still meet the goal of the carbon neutrality. So the opportunity for the advanced air mobility is clear. It's an opportunity of around noise reduction, CO2 reduction, and nitrox. This is enabled by the the industry 4.0 and all the latest development. We see that with all the actors actively taking advantage of all the latest technology to produce smaller, lighter, and more integrated parts. So that's all the opportunity that the advanced air mobility can take care of. Lithium-ion technology and batteries is part of these enablers for sure. But this is going to be always conditional to have safe and certifiable product. So this is kind of the intent of this slide, is to make sure we're passing through. Mission profile, the various application of various design, from full electric to a hybrid or to manned or unmanned applications, can be illustrated with all these this beautiful design that we see every day taking flight and making stride towards visibility. So again, lots of different mission profile, a lot of as a result, a lot of different requirements for the battery system. VTOL application here needs a lot of specific energy and specific power. Where the CTOL requires a decent amount of energy, but much less power. So these kind of graph start mapping the need and requirements of these applications. And when we start to overlay the capability of lithium-ion chemistry, we realize the feasibility of these applications. So for hybrid with extremely high power, very much lower specific energy, but needing a lot of power for since the application will require smaller cells, the ratio of energy to power is much higher. And so between CTOL, the conventional takeoff, the short takeoff, and VTOL, you can see that multiple requirements that can be met by different technologies. So here we presented solid state, which is going to be much later. Unfortunately, the readiness level of this technology, as we will see, is much lower than some other nickel oxide technology like NMC, nickel manganese cobalt, or LMFP, or which is lithium manganese phosphates, or some other technology that are very promising but still in development, like silicon anode and others. But I'll go a little bit more details on these with those chemistries. So if you kind of summarize the challenge of battery operated vehicles versus hybrid vehicles, you can map this kind of tables like that, where when you have specific energy, when you have can you guys hear me okay?
Yes.
Okay, all right, thank you. Sorry, I have no feedbacks. So specific energy is very challenging in the VTOL, as it's combined also with specific power, good cycling ability, and the form factor of the aircraft makes it, and all these factors of form factor certification and rechargeability makes the VTOL a very, very challenging application. CTOL and conventional takeoffs are much less stringent in their requirements. So again, this is a very very high level summary of challenges. But you can see what's interesting is to see the diversity of requirements between the hybrid and pure battery systems, or the different mode of flight. So during the design of these, to meet those challenges, the energy storage systems, seeking certification, has to focus on multiple what we call pillar of safety. The cell design was the selection of electrochemistries and the mechanical design of the cell. We'll see the results of these evaluations a little bit later in the presentation. At the system level, the thermal management is crucial for to make sure the chemistry retain its properties over its cycle life. And of course, there is all BMS and different electronics system around the battery to keep the integrity of the cell and the performance. The validation certification is, as you know, is paramount for verification of the performance and to make sure the product will perform over extended period of time and maintain its certification. And that is also the case for the manufacturing, that and process capability and the providing time after time a consistent product. That's the big challenge for the aviation. Here is just one of few of the multiple standards that are floating around these certification process for battery systems. VOS 311 and the appendix that are associated to it is a big one. DO 160 for the environmental and many others. So those are standards from industry that drives the verification of this safety house of around battery system. So if we take the battery system for VTOL and try to do highlights for lithium chemistries, the target is to be on the electrical performance is to be greater than 240 watt-hours per kilo. That's kind of a good number. Even it's challenging, but it's still a number that tries to be challenged towards higher figures, 2,000 watt per kilo. So combine and also offer 2,000 cycles. So these requirements and trying to meet these electrical performances and trying to meet DO 311A is or safety levels like UCAR, which is European standards for safety, a scale of 0 to 7, 7 being an explosive behavior, 0 being inert. UCAR 4 better is so it's a reversed scale, right? So low numbers are safer, high numbers are less more reactive. The industry also needs good maturity for this technology with TRL 6 or better technology readiness level, which is correspond to the validation. So it's after the prototyping, and you're entering the stage of validation and demonstration just before the manufacturing abilities. If I take various chemistries that I'm going to try to go through one by one, the very commonly used currently the nickel manganese cobalt, or NCA, nickel cobalt aluminum, which offer very high specific energy, specific power, good cycling ability, but unfortunately are more towards UCAR 6 or 7 exhibit poor safety, decent cost performance, chargeability is good, and the manufacturing ability is okay. If you the chemistry on the anode side, so the NMC and NCA is a cathode, so is your positive electrode, your negative electrode being carbon anode. On the LTO, the anode is lithium type, is a titanium oxide type anode, and allows for different behavior, different specific construction that allows for very hard charge rates and very high cycling. So that's the cycling ability is unmatched with over 20,000 cycles. But the low voltage makes this technology with very mediocre specific energy, good power capability. It's able to release its lithium very easily. Very good safety thanks to its very strong stability and the lack of certain characteristic in the electrochemistry. So can charge, be safe and powerful, but cost-wise is expensive technology, and voltage-wise, there's low voltage operational voltage, which makes it not so good for specific energy. The lithium manganese and lithium manganese phosphate, this is where we're going to focus today on, is a cathode technology. The carbonate, the anode is a carbon type anode with liquid electrolyte. So all these three technologies are liquid electrolyte. Is a good compromise of specific energy. So very similar voltage, operational voltage as NMC and NCA, because it's a blend of lithium manganese phosphate and NMC. So you recover specific energy very similar to the NMC. Very good power capability as well. Excellent cycling ability is very common, and the stability of the iron phosphate chemistry helps achieve level of safety of or exhibit level of safety of UCAR 4 or even 3 in certain conditions. So the good cost performance of the charge rate ability and manufacturing ability makes it a very interesting chemistry. In the future, that's why I placed that in parentheses, you will have some silicone doping on the anode that will enable even more specific energy. However, and this is why I keep it in dotted line, is that it's still a development technology for us and for the industry really overall. When you try to marry specific energy, specific power, because this technology, and due to properties of the silicone, is cycling fully, and so that's a challenge. The holy grail is solid state, with extremely high specific energy. However, because of the nature of the electrolyte being a solid phase, it is a challenge to achieve very high specific power. So for the industry right now of VTOL and advanced air mobility, this technology is still a few years away. So very low TRL, and that's also why I placed it in a dotted line like this. Good cycling ability and excellent safety, thanks to the no longer liquid electrolyte, solid phase prevents these liquids, these flammable liquids to be present, so enhance the safety. However, the lack of power is a crucial component for the for the availability of this technology at advanced air mobility. So when you see combined, you can see that LMFP is that blue line there is quite of a good compromise. So very quickly, the construction of NMC type technology, or NCA, what we call nickel oxide technology. So the very commonly used aluminum substrate onto which basically metal oxides are drafted on. So the NMC appears at the atomic level like this, where it offers layers where the lithium is encased. You've probably seen some very good animation of these structures. The lithium fully discharged, the lithium is kept on the cathode side, and when you recharge of potential, you're migrating your lithium onto the anode side, which is a carbon structure coated onto a copper foil. So if you were to talk to LTO, this will be titanate oxide instead of carbon, and then on the cathode side, you can have blend. So you can have LTO with NMC or LTO with LMFP or LFP as you wish. So you optimize and compromise and make selections of your component to obtain the characteristic you're trying to. The solid electrolyte interface is a very important component of the chemistry, partly using some of the lithium. So this is kind of this is basically capturing and making no longer available lithium, and it's passivating essentially the carbon anode. And this is one of the mechanisms of silicon technology, where these anode fractures, silicon SEI phase kind of gets recreated and consume more and more lithium, which makes you lose your capacity. So that's one of the difficulties of these. And the LTO technology, the lithium titanate, does not have this SEI, and that's one of the reasons why you can have very fast recharge, and you can obtain these very high cycling ability and very stable and very strong safety if that SEI is not there to be compromised and at risk. On the LFP, you'll have, instead of having a laminar structure like this on the cathode side, which is currently illustrated for the NMC, when you have LFP, the iron phosphates, you'll have the phosphate compounds that creates tubular structure that helps stabilize the cathode. And that's the safety enhancements that, so I can illustrate that here. So depending on what you're trying to achieve, energy, power, safety, cycling ability, or calendar life, if that's your application, you will take an advantage of these different chemistry. Like I mentioned, the LTO with no solid electrolyte interface, or the silicon anode that has very high interaction with lithium, carbon structure on the anode side, or on the cathode side, you choose laminar structures like the NMC or NCA, iron phosphates, or lithium manganese phosphates, which are different. They offer different structure. These two are what we call olivine structure or tubular structure. So they form tubes onto which the lithium kind of embeds itself. But the phosphate stabilize the electrodes. This is where the safety kind of gets improved from. Instead of having a laminar structure that can collapse and creates not necessarily stable compound. So if you translate that into a thermal runaway diagram of your various components, namely your positive and cathode, the separator components, and the negative or anode with its solid electrolyte interface, you basically have a total energy that is kind of a third, consider a separator and electrolyte being one. So you have a third of energy released through your cathode, through your anode, or through your electrolyte and separator. So mitigating safety being managing the risk, really mitigating all these components and all this behavior is crucial. So full thermal runaway. So you can the more heat get placed onto those chemistry, either from external or from degradation, internal mechanism, short circuits, or other failure modes. You will have initially a destruction of the solid electrolyte interface, which is, this is why it's important to note this structure into onto the anode. So as soon as you have destruction of this, you start a chain reactions of heat buildup that leads to other components to fail. Your separator can be next and leads to hard short circuit, which engage the cathode. When it's once the cathode is triggered, you have and that's, they're nickel metal oxide, so you have a lot of oxygen being released into the reaction. And once this is happening, now you have heat, oxygen, and fuel from your electrolyte, which enter this cycle of thermal runaway. Once you achieve, so the more charged you are, right, the more energy you have to compound these reactions. Okay, so but as soon as you have degradation of your substrate, which can lead to the aluminum, the anode degradation, and or your copper, you obtain metal fusion temperature, which are extremely damaging and extremely hard to stop. And this is why you see now that the processes of handling thermal runaway through immersion, or trying to drown the battery module with water, and some strategies like that, or letting it burn. So the benefit of having lithium manganese phosphates, or having a more stable cathode structure, is that you minimize a good third of these reactions. So that you can conceive degradation of your solid electrolyte interface, having some level of reactivity here. But if you have strong separator and prevent that cathode from reacting, you can obtain a much more stable system. So this is what we've done. Here is just a very brief overview. I mean, you're familiar with with a different format of cells, from cylindrical to prismatic, or a pouch. So each form of cell offer advantages and disadvantages. A cylindrical cell is a continuous electrode that is wound around a tube like this, a mandrel, and so that makes very little edges to the technology. So you only have the top edges and the beginning of the strip and the bottom. So that offers good stability of your layer to layer distances, which is crucial for lithium technologies. Extremely thin, and the distance between your electrode has to be maintained nominally, so that the lithium can move. It's a technology we call also rocking chair technology. You probably heard that terminology. Is because the lithium is going from one to the other electrode, right, from the cathode to the anode, and vice versa. And the discharge is going from the anode to the cathode. So having a nominal thickness structure and a good consistency is paramount to performances and life, electrical performances and life. But you can I mean, intuitively that on cylinder and on a tube like that, you create zoning of temperatures, which is a challenge for this technology, is to how to extract the heat, as we saw prior to that with the thermal runaway. Extracting the heat and the stability of your SE and your electrode is paramount. And so having a large cylindrical system sometimes a challenge to extract heat. Plus, a circle is not ideal for integration, as you're, side by side, you have some waste. So prismatic is interesting. However, it creates more edges. As you can see, there are multiple layers of like sheets in a book. So same challenges. These offer some mechanical structure. It's not completely ideal, but it offers and they're very dedicated systems. This one here illustrated here is a PHEV2 format that is very common now in the automotive industry. But that introduced the layer to layer of prismatic systems. The pouch cell is becoming more and more common now in the industry. Offers a very light packaging structure, weaker since it's a multi-layer of PVC and aluminum, and does not offer any kind of mechanical structure. So that you have to have an exoskeleton around the sail to maintain its mechanical integrity. However, this fragility is also an asset for safety behavior, since you can imagine trying to keep high pressure in a plastic bag is intuitively not happening, right? So that and it's effectively what's happening. So you're able to release your pressure and not like that. You have sometimes issues at maintaining in a prismatic or a dedicated system like that with very high mechanical shell around it. Even if you put mechanical safety release mechanism, I mean, you're still having chances to build up pressure and create very high pressure, very strong mechanical behaviors versus a sail that can release its pressure very quickly and therefore kill essentially its mechanic of thermal runaway. Just a very rough summary of the what we just discussed here, the value of cylindrical, prismatic, and pouch in terms of specific energy being me having very few mechanical structure. Pouch is much better in terms of specific energy. Safety, I was explaining the ability to release pressure, so it's good there. The prismatic format tends to be a good format to have fewer thicknesses, so therefore fewer zoning within the sail. So thermally, it's a good candidate as well. The return of experience and readiness is fairly equal across all this technology. The industry knows how to do that. Integration is very good for prismatic, a little bit more challenging for pouch, since you have to take into account its mechanical structure and maintaining shock and vibration. Very good for cylindrical. I mean, it's a circle, and so it's very resilient. So a little bit of a challenge here for the pouch. And the future proof also leads towards meaning which technology, the future proofing is which technology will come next, right? And as we saw earlier, the solid state being kind of the holy grail of technology. We believe that prismatic format will be of favor, since solid electrolyte materials are very hard. They're not very bendy here. So you have adding sheets and prismatic structure is much more likely. So this is my summary slide where I present the results that we've obtained with LMFP pouch cells. So an olivine structure with reinforcement of phosphates in the cathode, carbon anode, and the ability for us to achieve performances at over 240 watt-hours per kilo, over 1800 watt per kilo, and over 1500 cycle, and that's ongoing. So I think we should be able to do that. The highly noticeable aspect is the safety behavior, obtaining UCOR 3 and 4, which mean no flame and no ejection of materials. So the high integrity of the cell, and in several systems of sail and encased S&P's format, we were able to pass the DO 311 in terms of overcharge, over temperature, or short circuit. The readiness level, also the technology readiness level, is very good at as well, with multi-year, type of application experience and demonstration. So we gauge this at Tyrol 6 plus. I mean, we are actually manufacturing these cells on production line that are used for other pouch systems. So that's basically a manufacturing readiness level of 8 to 9, maximum being 9, which is full production, full commercial realization. And finally, the choice of or the selection of patch system to help with not only integration but thermal management, future-proof, and safety. So that's it for me. We can discuss a little bit more, and yeah, that was the opportunity today.
Thank you, Rodolphe. That's I'm sure that I have to go back to the material and the recording several times in order to make sure that I catch all the valuable information there. Appreciate that. It's a great overview and also dive into specifics. That was very much appreciated. Do have a question for you. Seems like you showed that on one of the chart, some of the strength and weakness of the different cell chemistries and packaging and so on. Does people, when I say people, eVTOL developer, OEM, whatever, try to combine two different technology? Maybe one has a high cycle, high specific power, but smaller total size mainly for takeoff landing, and the other one with a much better specific energy to control the overall weight of the airplane. Is that anybody doing that? Is that practical, or is that too complicated?
Yeah, so that's the challenge of this industry at this point, is that everybody's running for the entry in service and for their design to be certified, and people are keeping their design very close to the vest on the electrical integration side. What you're talking about is very interesting, and it's it could be considered in some ways. Electrically, it would be a very big challenge. You have to have redundancy systems. You have to have different potential different bus system that would have to be married, and so that would be a big headache on the power system side.
I would imagine, yes.
Yeah, because the problem with batteries is that it's chemistry generating releasing electrons, and each chemistry having a different potential curve, and that curve being changing over the state of charge of the battery, right? Therefore, you end up with potential difference, internal impedance changes based on different criteria. So temperature is one, state of charge can be one, the potential. So all these creates very strong, very big challenges. Transients between system is a bit of a nightmare.
Yeah. Okay. Yeah.
Especially at the very high voltage system that you have there. I mean,
right.
You're talking 800 volt typically on this. So I mean, it's I think with the advance of hybrid systems, they will have to, they are going to be challenged, because you have a generator, either you know, internal combustion engine or a fuel cell. So you're going to start facing these challenges, right? Because you're going to have multiple sources of energy trying to feed the motor system.
Yeah.
That I think this system will mature. But yeah, it's an approach. I mean, we see it in buses and vehicles, you know, electric vehicles, where they put supercapacitors in battery system. But it's a big challenge for chemistries, for battery and power systems.
Okay. Hey, JP, you got your
Hey,
hands
thanks.
up?
Yeah, can you hear me? All right. So, Rodolphe, thank you so much for your presentation. It was really meticulous and comprehensive discussion of the battery that I have ever seen. Now, I gave a talk in this working group a couple of months ago when I was working at the startup company doing building battery module and pack, not battery cell, for AAM market, and have a couple of comments about that. So just for the point that Johnny was asking about the hybrid system, there is actually one startup company called Our Next Energy in Michigan, who claims that they have built the hybrid system of LFP battery for early stage, and then anode-free battery, and they combined it into a one pack. So it's a claim. It's not verified yet, but there is an attempt in the industry. My question about that is, though, so you chose LMFP battery, which is a very interesting choice. But in terms of your discussion about the solid state being a holy grail, I think the name needs to be updated, because the core part of the solid state battery really is a lithium metal anode. That's what's important and gives you the better performance. Solid state electrolyte is more for the safety reasons.
Right.
And there are two companies out there already who claims that they can work with the lithium metal anode with the liquid electrolyte. So SES and Cuberg are those two companies, and they claim that they are fairly close to, you know, at the high TRL level, you know, in terms of the testing and the manufacturability and the scaling up process. So, you know, it's not just about your presentation, but it's industry-wide, I think, the issue that we probably need to update.
No, I mean, using lithium metal is Hydro-Quebec did that 20 years ago. You know, in the telecom industry, using melted electrolyte. So it's a solid at low temperature, and you had to energize the battery, you had to liquefy it. That was reutilized in France with a automotive manufacturer, you know, providing rent accessible batteries for accessible vehicles for rent. There's the solid state, and you know, is not one technology. You have many I mean, it's if nickel metal oxide technologies is vast in its choice of cathode and anode, the solid state is equally even more complex. So there is very different chemistries. I did not go in depth in that. We're working with a lot of different chemistries. Each chemistry offer you know, trade-off of I mean, you have some sulfur technology, you have some you have some hybrid, what they call a hybrid, where there's semi-solid electrolyte to help that conductivity. So I mean, I'm not surprised that you see out there technologies that are, you know, that claiming a lot of very high performance, and and are not necessarily exactly solid electrolyte like I was describing it here. I was just being very, very brief on that. And it is going to come. It's just for our discussion today on the advanced air mobility with entry in service 2024, 2025, a very aggressive desire to offer a service. I was trying to focus on the technology that are being used right now by the actors, namely NMC, NCA, NMC 811, and so on. And the chemistry that we were presenting here, which has this unique safety behavior, is also using NMC 811. It's a blend of these chemistry with the LMFP, which helps stabilizes. So it's just to show you the complexity of the discussion. As soon as we start talking about those chemistry, we're talking. It's like cooking a little bit. You make your chemistry and your flavor of to try to obtain. So we have a big say in our industry is optimize and compromise, and that's what that's a challenge is to optimize and compromise performances, safety, and try to have something that is scalable for manufacturing purposes and can be made available.
Yep, absolutely. Thank you so much. But can I ask you a follow-up question, Johnny?
Please do.
Okay, so another question I have is that you are absolutely right. So the industry currently, all the AAM OEMs are using MCA primarily, I think, with the Molicel cylindrical battery 45B. At least the companies who made it public knowledge. So Beta, Archer, many of them are doing that, even Vertical. You have made a comparison. You compared cylindrical cell form factor with the pouch form factor and come up with some of the advantages of the form factor. Some of them I agree, some of them I don't agree. But I was wondering, maybe you can tell me a little bit more about Saft having a big presence in the defense market, space market for a long time with a long history. I haven't seen any announcement of Saft partnering with the OEM customers in providing Saft batteries so far. And also the market has been dominated by Molicel cylindrical battery. And I was wondering if there's anything you can tell me about that.
Yeah, so we have a big presence, like you mentioned, with the traditional market. The lithium chemistry offers some challenges, and we are present on the A350. We have over 13 to 15 million flight hours on the Airbus A350 with 4 battery on board. We're present on the F-35 with 270 volt systems and the 28 volt system. So we're on board. We're on board satellite systems. So this is public knowledge. You can find all that on Saft. So the advanced air mobility performance requirements are quite unique, and as required us to rethink the chemistry. Our focus on safety and certifiability has prevented us from using straight NMC 811. So that's we have it available. We use it every day on Formula One and applications and other off-road mobility. But there is certain application where we were not allowed by our governance, our safety officers, to use certain chemistries, even though we may have used them in the past. Okay, so I think the decision and the delay of us having a full range of products already deployed is probably born in this. We are having technology release in the field. we're being very quiet about it. Those are strategies. I mean, I won't comment.
Okay, so well, thank you for your willingness to discuss this, especially in this forum.
We are but we are offering technologies for advanced air mobility. We are developing lithium-ion technologies for 28 volt applications and for like I said, for the advanced air mobility. We have multiple product range that are being designed. We are a commercial entity, so we don't necessarily go for prototyping. So this is probably why you didn't see, you're not seeing us with all these development, because we just don't. That's not our intention is to produce a product that is certifiable, safe, certifiable, performing for the long run.
Yeah, absolutely. It's gonna take a long time to be profitable with these prototype development. Thank you.
Challenging industry, challenging work, but I'm glad you guys working on this space, which give us some more confidence in the long-term progress and safety. I mean, I think we all agree that a certifiable safe product is really the key ingredient for AAM industry to flourish. Yes. So very much appreciate our speakers' insight, and I'm sure that we give a little more time, we can probably dive into way more details. And you guys have his contact information. If not, let me know. Yes. I'll make sure you guys get connected if you have more questions or input, want to have carry on additional follow-up discussion. I think, we'll absolutely, I will make sure you guys get connected. And with that, hey,
it was a pleasure. Thank you very much for letting me, for inviting me. Thank you very much, Donnie.
Hey, thank you so much. Again, as I say, I promise the high impact, a lot of information in the presentation. Very much appreciate that. I'll see you guys next time.
Thank you. Bye.
Thank you.
Bye-bye.
Thank you.